continue to join, but there is time for introduction. Today we are lucky to have Professor Quan Li. She is a professor at the Chinese University of Hong Kong's department, where she started to work at different levels of professorship since 2002. Dr. Li obtained her PhD in material science and engineering from Northwestern University, USA. Her research interests include quantum sensing for condensed matter physics, biomedicine, and energy applications. She is also interested in energy storage materials, specifically in situ and ex situ characterization of battery materials and processes. And also she works at the edge of nano-bio interfaces, specifically on nano-vaccine development for cancer therapeutics and autoimmune diseases. She has quite impressive list of honors and awards. Most recent honors include the 49th International Exhibition of Inventions Geneva Gold Medal, Croucher Senior Research Fellowship 2023-2024, and she was elected in 2021 a Fellow of the Royal Society of Chemistry. Quan, the stage is yours. We are looking forward to your exciting work.
Hey, thank you, Olga. Thanks for a very nice introduction, and also thanks for offering me this opportunity to discuss some of our works on this platform. Let me get my laser pointer. So I trust that everyone can see the PPT properly, right? And I shall be talking about the application-oriented nanothermometry using nanodiamond, and therein to discuss the opportunities and the challenges faced by the nitrogen-vacancy center-based temperature sensing. I usually put acknowledgement in the front, right, to address the importance of the people who contribute to this work, right? So the work I shall be discussing in the next 40 minutes or so were carried out in the CHK Quantum Sensing Group, co-led by Professor Renbao Liu and myself. And the credit really goes to our students and postdocs, past and present, and particularly to Zan, Junchen, who are currently in the group, and also our past students, Gangqin, Conway, Chufeng Liu, Wenghang Leong, and Ruqiang, who have either graduated or already acquired faculty positions in different places of the world, right? Also acknowledged funding support and our collaborators. So I guess for our small group of audience here, you are all quite familiar with nitrogen-vacancy centers. So I will skip the very basics, but just mention that the unique property, optical property of this NV centers in the piece of crystalline diamond really comes from the spin states of the ground state NV electrons. So one can basically optically polarize and read out the spin states, and also use the microwave to tune it. It's a technique known as the optically detected magnetic resonance, or DMR for short, right? But what is particularly relevant to the present application of thermal sensing, here I put down homotonia, and you see the most relevant term will be the first one. When you have this D, which is known as the zero field splitting, that represents the energy difference in between the MS0 and S ±1 state in the ground state NV electrons, right? And that value is temperature dependent, right? So if temperature gets larger, D value is getting smaller. Then in the corresponding ODMR spectrums, we expect to see that shift of the resonance deeps. And of course, later on, we're going to make use of the third term, which is the response of the NV electrons to the magnetic field, right? But I will put that to a bit later. So back to this thermal sensing using the first term. So if we're going to rely on the zero field splitting for the temperature sensing, one would realize the sensitivity will not be too great. All right, and here I put down some of the data that were measured from a number of nanodiamond particles. I believe this batch of particles are actually bought from the atoms. So we have a bit of the test over a few tens, even hundreds of nanodiamond, and we found this dependence of the zero field splitting on the temperature is about 74 kHz per Kelvin, which is typical. There's a bit of the spread, and that is you always expected, but the majority is around 74. Then in terms of the sensitivity of these batch of nanodiamond, again, they varied. I mean, this is very typical for nanodiamond samples, right? Each of the particles are different from one another. Then for the sensitivity, we usually can get in the range of a few hundred millikelvin to about a few Kelvin per square hertz, right? So the good ones can be in the hundreds of millikelvin, but the bad ones can even go to 10 Kelvin per square hertz. Right, so these are like not really great values in terms of sensitivity. But then the relevant question is that given that if we have a batch of ND like that, what are the possible applications? So this is actually our starting point. Now here, what I did is that I put down the comparison of the state-of-art thermal sensing technologies in terms of their probe size and the sensitivity. Now, as you can see from the far right end, the bulk diamond have a probe size comparable to that of the Raman and the infrared, but with superior sensitivity. But then the probe size or the spatial resolution can be improved if we're going to use nanodiamond to replace the bulk diamond, but of course, at some expense of the sensitivity reduction. But even for that, this sensitivity achievable by the nanodiamond is better than the green fluorescence protein or the germanium vacancy standards, right? And the most importantly is that for both the sensitivity and the spatial resolution of NV-based thermometry, there are still space to get further improvement. Right, when we argue from this map that the squid-based thermal sensing techniques will be the best in terms of the probe size and the sensitivity, which is true. But when one considers the working temperature range of the measurement, it becomes a different story, because we know the squid type of thermal sensing measurement only works in the very low cryogenic temperature. But then for NV-based quantum sensing, we have methods to make it work from very low temperatures cryogenic to usually for the common NVs, it works until 700 Kelvin. But recently we have developed techniques that can push it to 1400 Kelvin, right? And last but not the least, the NVs in the piece of diamond is very stable. This is not only referring to its chemical stability, so it can survive in the reactive environment, but also the photostability. So it's very suitable for the long-term monitoring of the temperature. Right, now considering all these features of the nanodiamond or NVs and nanodiamond, we thought it could be the most useful for two different systems. One is the chemical system and the other is the life system. For both systems shares a lot of things in common. Both of them would desire for the spatially resolved temperature measurement. For example, in a lot of the chemical systems, especially the working chemical devices, the presence of the local hotspot would affect the selectivity, reactivity, and the stability of the device performance. For example, here I put down an example of the lithium-ion batteries. The presence of the local hotspot was thought to promote the lithium dendrite growth and causing internal short circuit, so that shortened battery lives and even safety issues. Then for the life systems, it remains an argument whether there exists the spatial temperature variation in a single cell. then both the chemical systems and the life systems would have to face to the reactive environment that is always changing. Then, of course, these two systems are not exactly the same. Their requirement on the temperature sensing will be different in terms of sensitivity, the temporal resolution, and whether there will be a need of tracking these small sensors, right? Like in the chemical systems, we probably don't, but in the life systems, you can imagine when we introduce the nanodiamond sensors, they will be moved around in the life cells. So let me put to my first story, which is application of ND-based thermometry in working electrochemical devices. Well, to do this, we have set up ND-based thermal sensing system devoted to the operando electrochemistry. And the system allows a very easy switch in between the wide field and the confocal configuration. And thermal sensing can be carried out simultaneously with a number of electrochemical characterizations and other characterization techniques. We're still in the process of building up an entire system, but at current, we are already able to have some of the measurement carried out. Let me show you our first trial in a battery-like device. So this is a home-built device of a say miniaturized system simulating a battery process. So the battery process we simulated is the zinc iron batteries, right? We want to look at the zinc plating process. So in this setting, we have two electrodes, both of zinc, right? And they are soaked in the electrolyte, the zinc sulfate. And the nanodiamond sensors are placed at the bottom of the device in between the anode and the cathode. So now when we switch on the system, the electroplating of the zinc will take place at the cathode side. And the zinc will grow or be plated in the format of the dendrite. So you can see the dendrite of zinc start to grow from the cathode and move towards the anode. Now, at a certain point, it touches the anode, then the internal short circuit would take place, and that will cause a sudden current surge. And this current increase will cause temperature increase in the device due to the ohmic heating. But then as the dendrite of the zinc proceed, they might be falling off, small branches might be falling off from the main trunk. And also there are notorious parasitic reactions such as the hydrogen evolution will generate gas bubbles, and that will cause changes or damage in dendrite structures and thus affect the contact in between the dendrite and the anode. Then you would expect to see fluctuations of the current in such a process and thus fluctuation of the temperature. And that is something we're going to monitor. Now, to compare with the conventional thermal sensing method using either thermocouples, and here we adopted a PT100 type of resistant temperature detector. We placed on the outer surface of the device, and you can see the sensor head is actually quite large. It's about 1 millimeter by 1 millimeter that covers the entire region of the dendrite growth. Now, this is the data we got from the temperature measurement. On the left row, you see the shift of the ODMR spectrums, which is actually quite obvious in this process. On the right upper panel, I plotted 3 plots, right, with the current time evolutions together with the average temperature measured by the PT100 and the local temperature measured by a single nanodiamond sensor. Now, one can see both the average temperature and local temperature measured basically follows the trend of the current time change. But then if we look closely, we take the first derivative of the curves, we see there's always a few seconds delay in the response of the average temperature measured by the PT100. But then in the case of a nanodiamond sensor, it varies. In the specific case, we see a perfect match. In some other cases, we do see it happens in the form of delay or even happens ahead of time. So this is kind of indication of the spatial consequence of the thermal sensing or temperature, because the temperature we measured is actually determined by the heat generated and heat dissipated, right? So there will be spatial consequence of such a process. The most striking difference we observe from the spatially average temperature measured by the PD100 and the local temperature measured by the single ND is that when the current starts to increase until it saturates, the total temperature increase measured by the average temperature is about 10 degrees. But in the case of individual nanodiamond sensors, we see there's over 30 degrees increase. It's much more significant than the spatially average temperature. And such a phenomenon is also seen in a severe parasitic case when we have a lot of hydrogen bubble generation. You see there's a huge fluctuations in the current, and thus the temperature measured, both the spatially averaged and the local temperature measured by the ND. Right, and again, if you look at the total temperature increase, then the spatially average temperatures increases about 6 degrees, but then for the nanodiamond measurements, you see this is over 38 degrees. As a matter of fact, for over a few tens of devices that we've measured, the total temperature increase for the average temperature never exceeds 10 degrees. But then for the local temperature measured by ND is usually huge. It's usually a few tens of degrees. And the largest difference can be 1 order of magnitude. So 6 degrees, we can have 60 degrees increase in the locally. So this is to say, if we're going to use the conventional thermal sensing method to measure the spatially average temperature from outside of the device, this is very inaccurate. It's largely underestimated the local temperature increase inside the device, right? But then you say this is only one point. Now, how about other locations in the device? To do this, we have to switch to the wide field mode for the thermal mapping, right? It actually not as straightforward as we originally thought. We thought we just switch the mode, we can do it, but it turns out the zinc dendrite developed. Then if the laser hit the dendrite, it got reflected and re-excited the nanodiamond and caused large fluctuations in the photon counts. So eventually we settled with the turf mode so that the incident lasers only focus on the sensor layer without hitting the dendrite, and that kind of solved the problem. Right, now anyways, we got the map. So here I show the yellow cross, mark the location of the ND sensors that we selected. And the color bar tells the magnitude of the temperature of this measurement. So you see when the system was not started, the temperature in this device is actually low and quite uniform. When we switch on the device, you see temperature start to increase and the temperature non-uniformity start to increase as well. And this is better represented in this chart when I calculated the spatially average temperature from each of the single maps and plot it as a function of time. And you see it have sort of up and downs, but these up and downs kind of nicely match the change of the current, which is plotted in red in the same plot. Right, and the most interesting feature is that we also calculated the standard deviation of the temperature in each of the maps and plotted as a function of time. So the standard deviation of each of the maps in terms of temperature really represents the temperature spatial non-uniformity, right? And you see there's also up and downs, and these up and downs seems to have a correlation with the temperature increase and decrease as well. So that is to say, when the average temperature in this area of the device start to increase, then the spatial temperature non-uniformity also spread, also becomes large, right? And the temperature decrease, and the non-uniformity is getting smaller. And the maximum difference between two local points in this map can be as large as over 10 degrees. So this is not a very large map. This is only about 80 micron by 80 micron. And then again, we see similar things when the severe parasitic reaction takes place. You see much larger fluctuations in the current and thus in the spatially average temperature calculated from each of the maps, and also followed by the standard deviation of the temperature telling you the spatial temperature non-uniformity. But in such a case, the largest difference in between two local points on a single map can be as large as 20 Kelvin. So the temperature gradient is actually very large in such a small area. So let me move to the second story, which is the temperature sensing, in-operando temperature sensing carried out in the electrocatalytic cell. So being quite different from the previous case, which was carried out in the miniaturized device simulating the battery process. In this set of measurement, we are actually adopting real electrolyzer and carry out the electrocatalytic reactions in a practical condition. So this is how it looks, the side view and the bottom view of the electrolyzer. You can see the cathode, and this is the anode, right? And the electrolyte flow in and out. So the nanodiamond sensors are actually spread on the cathode, and with this enlarged image, you can actually see the wire, the copper wire for the microwave conducting through. Right. Well, the nanodiamond sensors actually can be plated on the cathode surface or the interface in between the cathode and the electrolyte. So that is the real reaction interface. Or it can be placed on the backside of the cathode to measure the backside temperature as well. We also, in order to make a comparison with the conventional thermal sensing technique, we also incorporated two thermocouples, one in the electrolyte, the other at the back of the electrode. The electrocatalytic reaction we selected is the very famous nitrate reduction that's supposed to produce ammonia, but then there could be a lot of other intermediate and other side products generated. And for the reaction we carried out, we actually have two major products. One is the ammonia, the other is the nitrate. Right, so this is a closer look at the electrode or the reaction interface. So the cathode was made of a piece of carbon paper with copper catalyst plated on this carbon paper. Then we add nanodiamond on top of it. And you see the nanodiamond morphology of these nanoparticles are very similar to that of copper, so that you won't be able to discern which is which in the scanning electron microscopy image. But then if you look at confocal, the emission of the nanodiamond can be detected, and we're able to control the density of the nanodiamond using the nozzle spray technology. Right, and here I show an example. We have actually a few hundreds, I think 400 or 500 nanodiamonds sprayed on this area. So it's about 120 by 120 microns, right? And we did a test on all these nanodiamonds in terms of the sensitivity estimation. So you see it have a wide range, right? The large ones can be even 20, but good ones are in the low single digit Kelvin per square hertz. So we did have a selection. We did not use all of them as a sensor. We choose 123 usable ones in this image, right? And the guideline is that we hope the sensitivity to be smaller than 3 Kelvin per square hertz. So that is a decent temperature that you need to catch out the important thermal event in this electrocatalytic cells. Right, so putting a lot of nanodiamond sensors might be a problem, but with controlled density, it doesn't really affect the electrocatalytic reactions. Right, and then here is the result I'd like to share with you. So you see on this chart, right, we have nanodiamond particles sprayed on the front and also on the back, and both can be measured. And we have also the thermocouples that are introduced in the electrolyte as well as the back surface of the electrode. So the temperature measured here I show in this chart, the thermocouple measurement are at the bottom. You see when the device starts, there's a bit of a temperature increase in the two thermocouples, one in the electrolyte and the other is the back surface of the electrode. But then the increase is really small, is about 0.5 degrees or even 1 degree, basically is negligible. But then if you look at the sensors, the nanodiamond sensors are placed either at the back surface and at the reaction interface. right? There's a huge increase in the temperature in the first 50 seconds. Then the temperature at the reaction interface actually stabilized at about 10 degrees. Then compared to this 1 degree increase, and again, this is very huge. This is 1 order of magnitude already. Right, and if we're going to increase the operating current from the 40 milliamp to 100 milliamp, you will expect to see even higher temperature increase. And again, in the electrolyte measured by the thermocouple, there's only like 1 degrees or so increase, but then here we have almost 20 degrees increase. Right, so why is that important, and what do we need that for? Now, in terms of the electrocatalytic reactions, what people know is that people would be quite confident to predict the amount of heat that are generated by specific chemical reactions. This can be done by measure the product of the electrocatalytic reaction, right? And then the temperature people can measure, but conventional people measure it away from the reaction interface, from outside of the device, and that's very inaccurate. And the problem is that the temperature is actually determined by the heat generated and the heat dissipated. And then the heat dissipation model at the interface is also not clear. Then now what we can do is that we can measure the temperature at the reaction interface in a very accurate manner. That means there's ways for us to figure out what is the heat dissipation model at this kind of interface. And that is very useful for the device designs and so on and so forth. So this is an ongoing project. We're still like on our way. The other part of the information that we actually can obtain from this thermal mapping is that, let me show you this video. Not sure why it's not working. Hold on a sec. All right, there we go. So this is a video showing the maps that will start. The reaction start at about 100 seconds, so it's going to start soon. Then temperature increase suddenly, and the spatial temperature non-uniformity start to increase as well. Right, so from this map, we actually have a lot of data. We're still struggle trying to dig out the useful informations. But let me just show you an example what we can do with that. Now, on the left panel on the bottom, here I can plot the spatially average temperature of all temperature points on this map, right? And you see a surge, then it's sort of a leveled off. We can also plot the standard deviation of the temperature in every one of the maps. And you see, again, it goes up with the temperature, then kind of stabilize, but then it still fluctuates a little bit, right? So this tells you the spatial temperature non-uniformity, just as in the previous battery case. But something else we also draw from this map recently is that if you look at the change of the spots closely, you will notice in some of the locations, it's kind of stable. It's not changing much. But in another location, it can flicker quite frequently. So we calculate or estimate the number of flickerings. That means there is a temperature either increase or decrease, right? And also other places, there might not be such an increase or decrease. So we look at each of the nanodiamond and plotted the temperature change as a function of each of the nanodiamond. What we found is that at some locations, for some of the diamond, they're quite active. There's a lot of up and downs in the temperature, but in other locations, it's quite stable. So that's a kind of an indication there exists the active site in this catalytic layer. And that was also remain as a mystery in the conventional electrochemical, electrocatalytic reactions. People suspect there are active sites, but there's no ways you can identify where are they. Right, so this is pretty much my story about the first application in in-operando thermal sensing carried out in the working electrochemical devices. Now let me switch to my second story, which is about the nanothermometry in live cells. Right, now compared to the previous case, which is more or less a ready-to-go measurement, the measurement or the thermal sensing measurement in live cells remains to be very difficult. Right, the reason lies in two key issues. One is the achievable temperature sensitivity in the live system, and the other is how we're going to track the nanodiamond sensors for its moving very fast in the live system. Right, here I list some of the literature works, right? So you see from the very early work back in 2013 done by Luking's group, when they demonstrate, which is really a proof of concept demonstration that NV-based thermal sensing can be carried out in the cells. And to later recent studies, people try to correlate the temperature measurement in the live cell and its physiological behavior of the live cells. Then what they found, or what people found, has been quite disappointing. The thing is that it seems there's not much correlation in between the temperature and the physiological or the pathological behavior of the cells. Now, the reason could be the sensor is not sensitive enough. The temperature change is actually very small to be caught by the nanodiamond sensors at the current stage. Right, so what we're trying on the other hand is try to improve the sensitivity of the nanodiamond sensors. This is actually a bit of earlier works that we carried out. So the idea is very simple. Now, just now I mentioned, if we're going to rely on this zero field splitting for the thermal sensing, the sensitivity will not be so great. But then we know NV is very sensitive to the change of magnetic field. So we thought if we're going to switch to the speed field response, that might be helpful, right? And the question now becomes, how are we going to create a temperature responsive magnetic field? And that will solve our problem. To create a magnetic field in the vicinity of the NV center in nanodiamond will not be very difficult. You just put a magnetic nanoparticle. The difficult part is that how to make it temperature responsive. Right, this very common idea is that if we're going to choose a ferromagnetic nanoparticle and to operate in a range close to its Curie temperature, that might work. This is because in this range, the ferromagnetic nanoparticle will change to paramagnetic. And in this region, it experiences a very large and sudden change in this magnetization. And that can be sensed by the NV centers in the piece of nanodiamond. So with this idea, all right, we have first get a try on the proof of concept demonstration in which we choose a bulk diamond and put the gadolinium particle on top of it. So without the gadolinium particle, what we see is that when the temperature changes for 20 degrees, you see about the 2 megahertz shift of this ODMR dips. But then if you put a gadolinium particle, you see the peak splitting, right? And then if you look at either the MS plus or -1 peak, you see there's a large shift in these peaks. So we plotted the data here. You see, again, over 20 degrees of the temperature change, the shifting of the either MS +1 or -1 can be as large as 80 megahertz. That represents 40 times increase, suggesting this method might work, right? But then gadolinium is not working because we cannot make it into a nanosensor. You make it nano, it will be all oxidized. So we switched to another system using copper, nickel, alloy nanoparticles. The nice thing about this particle is that copper and nickel are fully miscible in the full range from 0 to 1, right? And then given that the nickel is ferromagnetic, so you can have a Curie temperature about 600 Kelvin, and copper is non-magnetic. When you add copper in, you can reduce the Curie temperature and eventually drag it to cryogenic temperatures. So as said, this sensor would work the best in a temperature range close to its Curie temperature. In this way, by changing the X, you will be able to create a series of sensors that are working in whatever temperature you wish. Right, and this is how it looks like. This is a copper nickel alloy nanoparticle, and this is a piece of nanodiamond sitting next to it. So this is a hybrid sensor that we made, and you see in this hybrid sensor, we can achieve an estimate sensitivity about 11 millikelvin per square hertz. That represents about the 2 order of magnitude compared to, let's say, 1 Kelvin per square hertz for the bare nanodiamond. Now, using this hybrid sensor, we can monitor the real temperature. Here, we create a periodical temperature variation with the amplitude of 0.45 Celsius by modulating the laser power. And this was tracked using various acquisition times from 3 milliseconds to 15 to 30 and 90 milliseconds. And the 0.9 temperature variation is distinguishable with an integration time even at 15 milliseconds per data point. Now, of course, the problem with this kind of hybrid nanosensor is that this nanodiamond have poor coherence time, and there are a lot of MV centers in it. So the field gradient-induced broadening is also very significant. So all this can be overcome if we're going to adopt the pillar samples, which are provided by the Stuttgart group, right? They have very good coherence properties. And also because there are single MVs in it, so there's no gradient broadening anymore. And with that, right, we basically want to push the copper nickel alloy nanoparticles to the vicinity of the nanopillar samples. And what matters is that the location and the orientation of the magnetic particles relevant to the pillars is also very important. So by using the AFM tip to manipulate these particles a little bit with the pillars, we can adjust it to the right position to achieve the largest temperature susceptibility. Now, in this one, we can achieve a sort of temperature susceptibility at about 47 megahertz per Kelvin, right? And that represents a few hundreds of times of increase in terms of the sensitivity. If you consider the original dt, the zero field splitting is only 74 kHz per Kelvin. Now, in this one, we're able to obtain short noise limited sensitivity at about 87 microkelvin per square hertz. Now, with that, what we can do is we can have a very, very good capability to measure the millikelvin temperature dynamics with a temporal resolution about milliseconds. Now here I show a histogram of the uncertainty of the temperature measured with a sampling time of 5 milliseconds. Now you see this distribution basically is a Gaussian with a standard deviation at about 1.5 millikelvin. As a comparison, for the same measurement to achieve the same precision, if we're going to use the previous nanoparticle sensors, we're going to use an integration time of 50 seconds. Right, and that brings to the discussion whether this kind of sensors can be used to the biological system. And it turns out to be not so straightforward. The reason why is that, remember, I mentioned one of the merits of the nanodiamond is that it's very stable. And also for the biological system, it has very low cytotoxicity. But now we're making a hybrid sensor. So the sensitivity is improved, but then the stability as well as the toxicity issues will come up. So whenever you make small changes, other things will change as well. Right, and that brings to bring my talk to the last slide, which is a short summary. What I have been discussed in the past 40 minutes or so is really about the features of the NV-based thermal sensing. We show that the thermal sensing has accessibility to the specific locations, is very stable, and have very good spatial resolution, make it suitable for both electrochemical devices and life cells. Now, however, for the current bare nanodiamond, right, the sensitivity and the temporal resolution is already good enough for measurement to be carried out in the working chemical devices. We can readily use it and getting some interesting results. But then for the live cell measurement, we're still quite far. In terms of sensitivity, if we're going to use the BioND, we're a few order of magnitudes away. We might have solutions either by introduce the hybrid sensors or maybe by some protocol controls. The sensitivity can be improved, but then they're not suitable for the live system. Now, with that, I have to say there will be still a lot of work to be done in order to make the thermal sensing can be really carried out in live cells. And with that, I would like to thank all of you for your attention.
Quan, thank you very much. A very unique, interesting presentation. We are open for questions now. You can unmute yourself and ask your question in person or type it in a chat, and I will ask it.
Hi, so I had one question about how you were dispersing, I guess in the first part of the talk, how you were dispersing the particles on these little different reactors and how the particles are actually interfacing with the surface.
So you're talking about how the dispersing was carried out in the electrochemical devices?
Yes, exactly. And like, the context of this is that you said that you were maybe seeing like potentially different catalytic sites, some that are active and some that are not, and that's kind of related to the heat that you're measuring.
Yeah, right. So first,
could that at all be related to how the particles are, contacting the surface?
Yeah. So first of all, the surface of the or say the interface of this reaction is not like a flat interface. So basically, it's composed of layer. I think I better go back to the previous slides. So they are made of catalyst nanoparticles. So here on the one I mark in the green, you see these are the catalyst itself. So basically, they are copper nanoparticles with a size of a few tens of nanometers to hundreds of nanometers, right? They are actually sprayed on the carbon cloth, right? So this interface is not like an atomic flat, or it's not flat at all, right? Then we just disperse the nanodiamond on top of it. And the dispersing method is the something called nozzle spray. I don't know if you knows about it. So it's a nozzle, then there's a gas to push from the back. So it's basically sprayed out on the surface. We tried before many different methods like spray coating or things like that. The nozzle spray is probably the best to have very uniform distributions, and by controlling the density of the nanodiamond, or say the concentration of the nanodiamond, the solution, the density can be controlled quite nicely, right? And then in terms of the interface, if you look at the SEM image after the nanodiamond was sprayed, you actually cannot tell which is nanodiamond, which is copper. So, but if we look at the confocal, so we can change the focal point, focal length a little bit by shifting the Z. So we actually see nanodiamond are at different Z height. That means some are more on the top surface, some are going a bit inside because the surface of this catalyst is not flat at all.
Okay.
And maybe follow-up question to this previous question. Do you observe some aggregation of nanodiamonds? Is aggregation a problem, and how do you avoid it? Do you try to adjust nanodiamond surface, for example, use polyglycerol coatings on nanodiamonds to make them more stable?
For the biological systems, yes, we do. Well, actually, I think I should put it this way. If we're dealing with nanodiamonds with a size of about high tens or hundreds of nanometers, the aggregation is not significant. right? By controlling the concentration in the solution, you don't get much of the aggregations when you spread it on the surface or introduce to the live cells. There's not a lot of aggregations at all. But then if you go down to smaller size of nanodiamond to reduce it to, let's say, 30 nanometers or so, aggregation becomes a problem. They are likely to get together a lot. Then in the literature also on ourselves, you can do some coating on this nanodiamond, right? Chemically, that helps a little bit. And also the chemical environment also matters. Like especially when you try to introduce the nanodiamond into the biological system, it depends on when you feed to the cells, what kind of solution what kind of medium are you using, right? So PBS or you're going to use FBS or whatsoever. So all that matters, right? Then for this catalytical device application, we are actually using nanodiamond with a bit large size, so high tens or even hundreds nanometers. The reason is because we're not trying to look at very small areas, or we're not capable of looking at very small areas at the moment. So we need, especially for the mapping, right? The best resolution we can obtain is the optical resolution, right? So it's not determined by the size of the diamond, but by the size, but determined by the diffraction limit, right? So if you put two nanodiamonds too close together or making them very small, it's not very helpful, right? So in that case, we can sacrifice, we can use larger nanodiamond, then aggregation is not a big problem anymore.
I'm also curious, what is acquisition time in your measurement for these electrochemical devices? How long each measurement?
For the
takes?
temperature sensing, right? The fast ones can be 1 to 2 seconds. Long ones can be 6 to 10 seconds. So it depends on what's the requirements on data quality. So we're using 3-point method. If one use a full spectrum, there's no way. That would be too slow.
Did you talk to some integrated circuits developers if they are interested in nanodiamond for their R&D? Did you have a chance
Not
to talk to
really.
some practitioners?
Yeah, I haven't found very suitable collaborators in that area. Earlier, we're looking for like a nano device, but then we realized it's kind of awkward. Nanodiamond is not small enough for these nano devices, because for people working on carbon nanotubes, and then for a single device, they have a lot of carbon nanotubes, the contact and everything. They actually care a lot about the thermal dissipations and everything. But then they are looking at a length scale in terms of a few tens of nanometers. But then for our nanodiamond, the size is about 100 nanometers. So it doesn't really work, right? But then for a larger scale, like conventional devices, I haven't really explored that directions.
Good. It seems that results are quite impressive, and new unique information is available.
Yeah, I think
Yeah.
for the chemical devices that we're working on at the moment, we do get quite a bit of interesting results. And it seems, even with the current stage of a nanodiamond, people can do something about it.
We have a question. Alex, please ask your question.
Thank you very much for very impressive presentations, very interesting results. My question concerns one of the first slides, where you represented the spin Hamiltonian. May we start with the second or third slide, the spin Hamiltonian.
Which one?
Yeah, even before. Yeah, and another slide back. Yeah, this one.
This one?
Yeah, this one. My question is, you wrote here the terms of spin Hamiltonian, and the first term you wrote is responsible for temperature and pressure, and second for electric field, for sensitivity to electric field. Frankly speaking, I didn't understand it, because D and E terms, both of them represent the same zero field splitting. And if their field splitting is sensitive to temperature, pressure, or electric field, both these terms should be responsible for this one. You cannot separate that this term is responsible for temperature and pressure, and this specific term, the anisotropy of zero field splitting, is responsible for just for electric field. Both of them are correlated, because it's,
yeah, of course.
the separation into two terms is just a kind of representation, not more.
No, this is just for easy correlation of the usual measurements that you ascribe to. And there's cross correlations, like even if you measure the magnetic field, whether they will have a temperature term on terms of the shiftings, there are. So it's not like you solve this. So the idea of listing this is for illustration, not to say.
Okay, what about the specific electric field sensing? Is it possible at all? Or just for electric field sensing, you need something of quadruple terms for spin Hamiltonian, or something like this one?
I think for electrical field sensing, it depends on what do you want to sense. People have to make estimations like how large is the E field before nanodiamond can give a valid signal. So it's not about whether it can sense or not. Physically, the principle allows if there's a response, but whether you will be able to make the measurement, it depends on how sensitive it is.
Okay, I understand. Thank you very much. Thank you.
Do we have more questions?
I have a question about when you were showing the data with the battery measurements. So you were comparing the temperature change that you were able to measure with the diamond particles versus, say, an average temperature from a thermocouple. But then you were also showing current measurements. So my question is, surely like comparing the thermometry with the diamonds with the average thermocouple measurement, it shows an improvement, but how does it compare to the information you can get from, say, monitoring current? Because it seemed like you were showing, here there's like a good correlation between the current and on the first derivative with the diamond. So what is the advantage of using the diamond in this case if you could also get the information from the current? And in terms of sensitivity,
Yeah. I mean, the biggest difference that we see from here is that, of course, you can always measure the current, but then from the current, you don't know what is the temperature. The thing is that you cannot like directly incorporate the current to a value of the temperature. But in the battery, for example, what really matters is like how high is the temperature. Like if it's within 100 or so, or within, let's say, 50 or so, people doesn't really care too much. Well, it might cause some of things to happen, but it's not like it's going to cause catastrophe. But then if you trigger it at about 120 or so, thermal runaway will take place. So there will be a chain reaction going on. So you can, from the current, you can read, okay, there's like a temperature increase, right? If it's, and again, in this process, because the origin of the heat is coming from the internal short circuit, so that's the ohmic heating, right? And that's why you have a direct correlation with the current, right? But in other cases, there are the resources of the heating source, then there might not be like a direct correlation with the current. That's one thing. And even for this current, go back to my previous argument, you don't know what exactly the temperature. Now, it's the same thing for measurement using the average temperature using PD 100, you hope to measure a temperature, but that temperature is not accurate. It's largely underestimated. So you thought there's an increase in the battery for like 6 degrees that can be totally negligible. It doesn't matter. But then if it's inside is 60 degrees, that's a quite different story.
Mhm. Mhm.
Okay, great.
Yeah, so like practically, I'm just do you, I mean, I guess somebody studying battery, they need to know that temperature. They couldn't just like look at, say, a current runaway and say, okay, something clearly went bad, and it's like
No, not
yeah.
really, not really. They can't.
Mhm.
Current is part of the contribution to the thermal process, but not necessarily.
Mhm. Okay, all right, thank you.
Any more questions? Please feel free to ask. It looks like, yeah, we have quite a few questions and people are satisfied. And Quan, I would like to thank you again for your great presentation and wish you luck in your future research.
Okay, thank you.
Okay. Thank you everybody for attendance.